Hey, who likes lenses? Alrighty, so here we go. We got a converging lens here and a diverging lens down here. You might say, hey, but why is that a converging lens? Because when this material is more dense than the material around it, when light enters, it comes towards the center. It converges to some point, some focal point. Light, if this is more dense than the surrounding material, light coming in actually bends away from each other, or it diverges, hence the name diverging lens. Okay, so there you go. So yes, it is a convex lens, but the reason I like the term converging is because if this material is actually less dense than the surrounding material, it does the opposite. It turns it into a diverging lens. I don't know if I said mirror, but I'm talking about a lens here. So it's a better term to say converging lens than necessarily convex. Alrighty, let's get started here. Alrighty, so a couple things. Special name for this thing in the middle called a principal axis. There's your vertical axis right through the converging lens in this case. Yes, it's convex. And this is the focal length, the point where light would focus if light was coming from the right to the left, and there's one just on the other side if light was coming from the left to the right. And there's another point 2F, which is simply there as a marker to give you a reference point. And you'll see why it's a helpful reference point. Nothing really gets necessarily focused there. It can be an image there, but an image could be focused at a lot of different places. But it's a helpful for a transitional phase, and you'll see that in a little bit. Okay, so we didn't do the mirrors yet. We'll get there. We just did refraction, so I thought, yeah, let's do lenses first. So that's what we're doing. So there's a principal axis that we talk about going right through the middle of the thing, and there you go. And there's a 2F, and yeah, I think I just talked about that. All right, let's keep on rolling. So a couple things. So in this case, they're not really showing you over here, but let me just go ahead and put in an object. Let's do a red object. So right here, there's a red object I thought I was drawing, and I guess I wasn't. Let me try that 7 more times. Pen. Okay, so let's say this is an object right over here. Boop. Maybe a lollipop, who knows? But light bounces off the top of that lollipop, stuff coming straight in. So light coming parallel to this lens gets bent into this thing and then gets bent some more through a focal point. Light that would be coming reflecting off the head of that lollipop through the focal point gets bent some more and comes out this way. It turns out that it doesn't matter if we do all these little refraction points on the inside or we just skip it. It's a lot easier just to do this skipping all the little things and just do the approximation. It's the thin lens equation thing rather than using this fat lens and doing all the little bendy stuff on the inside. It's much faster. Okay, so we're going to just, when doing our ray diagrams, we're just going to use the thin lens approximation of the thing. And we're going to learn about what different rays we can draw here. And the other ray we're missing is the one that's going right through the middle. If there's one through the middle, it doesn't bend at all. And boo, there's your image. Notice that if you're outside the 2F, it's inverted and smaller. So it's demagnified, or the magnification is less than 1. And it's going to be a negative magnification, meaning that it's inverted. So whenever the object is outside the 2F, even though it's not a focal point, we just have that as a reference. You're going to notice that the image will be real, because you could put a card here or some kind of a wall right here, and it would focus the image. It would be smaller, but it would be upside down between the F and the 2F. And the same thing happens over here. It's no different. Light would come right through the middle. And sure, there's some bending that happens coming through there, and there's some unbending. Whatever happens, it's still going to hit the same point. And there's your upside down lollipop person or whatever that thing is. Okay, I didn't do all the proper bending, but we got other stuff to do today. So, get rid of that pen and keep on rolling. Alrighty, So let's talk about all the ways that light comes in and how it focuses. So whenever you have light coming in parallel to the converging lens, it's going to bend into the focal point. So any light coming in parallel, boo, going to hit a point. So the quick and dirty way to find the focal length of a lens is you look at something far away. Because something super far away, the light is coming in pretty much parallel. If something's closer than that, like maybe over here, light is not coming parallel. So, but something super far away, even though it's technically not parallel, it's pretty close to parallel, and that's close enough to the focal point. So, lines coming in, light rays or photons coming in parallel, get refracted towards the focal point. Now on the other side of things, you could put a light bulb at a focal point right over here, and light would shoot everywhere, but the light coming towards the lens from whatever angle, doesn't matter because it came from this point, light coming from this would hit the lens and come out parallel. Just as parallel light comes in and goes to the focal point, anytime that light shoots out of here, and it's not just those 2 points, okay? It's all these points. I mean, it's even light coming out in this direction, boo, shoots out parallel. Light coming out in this direction, boo, shoots out in parallel. Light coming out in this direction, boo, shoots out in parallel. Light coming out in this direction, boo, shoots out parallel. Light coming out in this direction, misses. That was a terrible shot. I don't know what happened there. Maybe it's a warp in space and time. But the point is, you could put a bright source there, like a light right there, and this would actually not focus the light, but it would point all the light in a single beam that does not spread out. Kind of like in those police search headlights, you know, and they could put them on the car and they could bend around and look at different things. Alrighty. And down here at the bottom, any light coming in, so let me get the drawing on. Well, I'll keep the drawing on. Any light coming through the exact center, sure, there's a little bending that happens, but the point is it still comes out by the way it curves there compared to it curves over there. It comes out at the same angle over there. So even though it's a slight bending on the inside, it comes out at the same angle passing through the middle. So it's alike, it doesn't get bent at all. Okay, it's called the thin lens approximation, and it works good enough for most all of our lenses. Okay. All right, got rid of the pen there, and let's go to our next slide. Alrighty, so convex lens beyond the 2F. We actually did one of those already. Okay, so there's 3 rays you can do to find out exactly where you're going to find that image. Okay, 3 rays, count them up, 3. So, and one could be, boo, look at that. That was quick. So that's the parallel stuff. Remember, anything parallel is going to come through and going to be bent through the focal point. Well, another one you could do is, woo, right through the focal point. And then anything going through the focal point, remember, like going through the focal point, goes out parallel. Now, the one they didn't show you, let's see if they show you on this one. Oh, they didn't show you, but there's some magic there anyway. The one they didn't show, there is a third one they could have done, is the one that's straight through the middle. The one going straight through the middle goes through pretty much unbent, hits the same spot. So you notice that it's inverted and smaller. So whenever you're outside the double F or the 2F, the object is the magnification that's smaller than the original, so it's less than 1. It's going to be a negative magnification, meaning that it's inverted upside down, and it is a real image. You could put a piece of paper there, and it would focus the image right there. Alrighty, let's keep on rolling. My face is frozen on my screen. I don't know about yours. We'll see what happens in the end. Maybe you have to do it all over again. That would stink. Alrighty. Hey, what if you're between the F and the 2F? What happens? Click. Well, there you go. Let's do another click. There you go. So right through the focal point right out there so we can see where the object is. Now what they skipped is the third one. I like to do 3 just for fun, just to triple check sometimes. And that would go right through there. Sometimes I'm in a hurry and I just skip it because I know it should go right in through there. And there you go. That means that object's going to be way over here. Whoops, I missed a little bit. There's your object. Okay, well they're going to show you a better job than what I just did, hopefully. Alrighty, so the object is inverted, and larger. So the magnification will be greater than 1. It'll still be negative because the negative means it's inverted, but it's going to be greater than 1 because it's larger than the object. So the negative just means it's inverted. And it's a real image. You can put a piece of paper there because light focuses on this thing. Not just here, guys. It focuses everywhere. We could do the belly button and do the same rays and it'd focus right over here. We could do the toes right over here and find out they would focus right over there. It's just faster to do one spot only. Okay? So there you go. So when you're in between the F and the 2F, it's larger, but the image is outside the 2F. Okay, well, there's one more place, 2 more places to go. I don't think they're going to show you on the F, but we'll see. All right, next slide. We're on the inside. Okay, here's the one they didn't show you. So let me go ahead and show you the one that's right on the F. Okay, so if you're right on the F, and we use an arrow because they're using an arrow. So light comes in, boo, through the focal point, right? Well, what if light was coming right through the middle? Boo, hey, how do those two lines compare? They're parallel. And I can't really draw one through the focal point because I'm there. So where's the image? Well, guys, there is no image because these lines are parallel. They never come together. Even if there's an eyeball over here looking at all this stuff going on, a big red bloodshot eyeball looking at this stuff going on, they're seeing the object at infinity. There is no object whatsoever to see. There's nothing to focus. There's no image there whatsoever. And so if you were to put your eyeball at the focal point of a lens, you're not going to actually see anything because this is going to be a big fat blur at that point because there's nothing to focus. Now, this one is going to be right at that spot over there. So let's go ahead and see if I can erase all the ink on this slide. There we go. Alrighty, so let's continue on with what's going to happen when we're inside the focal point. There it is, guys. Whew, that was quick. How about another one? Ooh, did you notice that was a little different? So we're still use the focal point on this side because if light was here, if light was coming out of that focal point, it would follow that and come straight out there. That's what would happen. So light from that direction comes straight out, but you notice it's diverging. How do you make an image? And I don't know if they're going to do the third one. Nope, they're not. So if I wanted to do that third one, because they seem to hate that third one, the third one is straight through the middle. So if I do the third one straight through the middle of this thing, it's also diverging. They're all spreading out. It's not parallel to this one. They're all diverging. Dios mío, where is the image to this thing? Well, it's backwards. Because what happens is you follow the line of sight backwards. Because if I have a giant eyeball over here, and I don't have to have a giant eyeball to see this, but pretend that's an eyeball. The reason I'm drawing this is to show you that these 3 rays, the eyeball can act as a lens, because there is a lens in the eyeball. It can actually focus an image and still see something. But where you're going to see the image is right back there. Because we don't see the curvy nature of things, because there's no image over here because that's diverging light. The image that this eyeball would see on the other side of the lens is back over here. That's what a magnifying glass does. So you put this convex lens near some object right over there. That object is on the inside of the focal length. Whenever that object is on the inside of the focal length, it's going to make it look large. There's no object really there. It's a virtual image. There is no light focusing here, guys. There's no light focusing. The light is diverging on the other side. There is no light there. It's a virtual image. And it's upright. It's erect. So the magnification is a positive, and it's greater than the original size. And it's located beyond the F, but there's actually no light over there. Okay, so we're going to have to pause right there and pick up at this spot because I'm at my 15-minute limit for the old YouTube. Praise be to YouTube.